In the summer of 2021, a factory in Michigan that had been building trucks for 57 years went quiet, not because demand collapsed, not because workers went on strike, not because management made a bad decision. The factory stopped because it couldn't get a chip that cost 87 cents. A microcontroller smaller than a fingernail, designed using technology from the 1990s, running instructions simpler than the first iPhone. Without it, a $55,000 truck was an unfinished assembly of steel and leather sitting on a production line going nowhere. Ford lost an estimated $2.5 billion in revenue that quarter from semiconductor shortages. General Motors pulled $1.4 billion from its annual earnings forecast. Toyota, Volkswagen, and Stellantis reported similar disruptions across 3 continents simultaneously. The global automotive industry lost approximately 7.7 million vehicles in production that year, not from a war, not from a financial crisis, not from any visible catastrophe, from a shortage of components that most technology analysts had stopped paying attention to years earlier, because the semiconductor conversation had moved on to bigger things. 5-nanometer chips, 3-nanometer chips, artificial intelligence accelerators, quantum computing architectures, the chips that power the future. While the world focused on the brain of the digital economy, it forgot about the nervous system, and the nervous system is where the vulnerability lives. To understand what a legacy chip actually is, it helps to start with what the term means. In semiconductor language, a chip's sophistication is measured in nanometers. Nanometers describe the size of the transistors etched onto the chip's surface. Smaller transistors mean more computing power in less space, consuming less energy. Today's most advanced chips use 3-nanometer processes. A human hair is approximately 80,000 nanometers wide. A 3-nanometer transistor is so small that fitting concepts from classical physics to describe it requires quantum mechanics. These are the chips that power artificial intelligence systems, high-performance computing, and the most advanced smartphones. They represent the absolute frontier of human manufacturing capability, and they receive almost all of the political attention, the investment analysis, and the strategic discussion about semiconductor competition. Legacy chips use processes of 28 nanometers and older. Some use 45 nanometer, 65 nanometer, 90 nanometer processes. By the standards of frontier semiconductor manufacturing, these are ancient technology. They are also in almost everything. Your car contains between 1,000 and 3,000 semiconductors. The majority of them are legacy chips. They control your braking system, your fuel injection, your airbag deployment, your power steering, your transmission, your climate control. None of these functions require the computing power of an AI accelerator. They require reliable, rugged, proven chips that can operate across extreme temperature ranges, tolerate vibration, and function without failure for the decade-plus lifetime of the vehicle. Legacy chips have been doing exactly that for 30 years. Your refrigerator has a legacy chip managing its compressor cycle. Your washing machine has one managing water temperature and spin speed. Your industrial HVS system has several managing airflow and energy efficiency. The power grid substation in your city has dozens managing switching and load distribution. The medical devices in your hospital have them monitoring patient vitals, managing drug delivery, controlling imaging equipment, and the weapon systems in your country's military inventory have them too. The F-35 Lightning II, the most technologically advanced fighter aircraft ever built, contains approximately 3,000 semiconductors per aircraft. The majority are legacy chips, not because the defense contractors didn't want advanced chips, because advanced chips aren't appropriate for the job. A fighter jet requires chips that function at temperatures ranging from negative 55 to positive 125 degrees Celsius, that survive vibration loads that would destroy consumer electronics in minutes, that operate reliably for decades without access to maintenance or replacement. Legacy chips, hardened for aerospace applications, meet these requirements. 3-nanometer chips optimized for data center performance do not. This is the first irony at the center of the legacy chip story. The United States has invested hundreds of billions of dollars in maintaining the frontier of semiconductor technology. The CHIPS and Science Act committed $52 billion to advance domestic semiconductor manufacturing. Taiwan Semiconductor Manufacturing Company is building facilities in Arizona to produce leading-edge chips on American soil. Intel is investing $100 billion in advanced manufacturing capacity across multiple U.S. states. All of this investment is aimed at the most sophisticated, most advanced, most powerful chips available. And none of it addresses the chips that turn the lights on, start the engines, and fire the weapons. Because those chips, the legacy chips, the humble microcontrollers and power management units and analog interface chips, come overwhelmingly from somewhere else. The numbers are not subtle. In 2020, China accounted for approximately 23% of global legacy chip production. By 2023, that share had grown to approximately 31%. By early 2026, estimates from the Semiconductor Industry Association place China's share of global legacy chip manufacturing at approximately 80% of new capacity additions over the past 3 years. While the West built fabs for 3-nanometer chips, China built fabs for 28-nanometer chips, dozens of them, subsidized by the Chinese government at an estimated $30 billion per year in direct and indirect support. The strategy was deliberate, documented, and hiding in plain sight while Western analysts debated export controls on advanced chips. To understand why China chose this approach, it helps to understand what the advanced chip sanctions actually accomplished. Beginning in October 2022, the United States implemented export controls preventing the sale of advanced chips and chip manufacturing equipment to China. The controls targeted chips used in artificial intelligence, high-performance computing, and advanced military applications. The stated goal was preventing China from developing AI capabilities that could be used for military modernization, surveillance infrastructure, and advanced weapons development. The controls were genuinely consequential. NVIDIA's H100 chips, the primary hardware for training large AI models, became unavailable to Chinese customers. ASML, the Dutch company that makes the extreme ultraviolet lithography machines required for manufacturing chips below 7 nanometers, was restricted from selling to China. Without those machines, China cannot independently manufacture the most advanced chips. This represented a real technological constraint, but it also represented a strategic choice that China could work around by going in a different direction entirely. If advanced chips were sanctioned, China would dominate legacy chips, not as a consolation prize, as a deliberate strategic position. Because the question China's planners asked wasn't, how do we get the most sophisticated chips? The question was, what chips does the global economy actually need to function? The answer pointed directly at legacy semiconductors. The Chinese government's Made in China 2025 plan, which Western analysts initially focused on for its AI and advanced technology ambitions, contained a quieter objective: achieve self-sufficiency in legacy semiconductor production and expand export market share. That objective received approximately $150 billion in government support between 2015 and 2025, spread across dozens of Chinese chip manufacturers. Companies like SMIC, Huahong Semiconductor, and Nextchip built out production capacity at 28 nanometer, and older nodes at a pace that no private market would have funded. Because the economics of legacy chips, left to market forces, don't support massive new investment. Older fabs have largely depreciated their equipment costs. Prices are low, margins are thin. Building a new 28-nanometer fab using market logic doesn't make financial sense when existing capacity already meets demand. Unless the goal isn't financial return on a single fab, the goal is market control. Hint, market control at below-market prices is exactly what government subsidy enables. By 2024, Chinese legacy chip manufacturers were selling microcontrollers at prices 30 to 40% below equivalent products from Japanese, European, or American competitors. Not because Chinese chips are better, because the production costs are subsidized below the level any private manufacturer could sustainably match. Automotive supply chains, which operate on margins of 3 to 5%, cannot absorb a 30 to 40% price disadvantage on components. Procurement managers doing their jobs responsibly shifted sourcing to Chinese suppliers. Tier 1 and Tier 2 automotive suppliers restructured their vendor relationships. The transition happened gradually, rationally, invisibly, driven by normal procurement logic. And by 2025, that transition had progressed to the point where disrupting Chinese legacy chip supply would create an automotive crisis comparable to or larger than the 2021 shortage. This is the trap. Not a sudden seizure of supply. A gradual consolidation so complete that any disruption, whether from geopolitical tension, export controls, or deliberate restriction, creates pain that the West has no short-term way to absorb. The automotive industry illustrates the mechanism. Defense supply chains illustrate the stakes. A Raytheon Tomahawk cruise missile contains over 400 semiconductors. An Army Patriot missile battery uses chips in its radar systems, its fire control computers, its communication equipment, and its launcher control interfaces. A Navy Arleigh Burke-class destroyer has tens of thousands of semiconductors across every system, from navigation to weapons targeting to damage control. The Pentagon has publicly acknowledged that its weapons systems depend on semiconductors sourced from foreign suppliers, including suppliers in countries that are geopolitical competitors. The specific sourcing details are classified. The general vulnerability is not. In 2022, the Department of Defense released an unclassified summary of its semiconductor supply chain review. The summary noted that the department had identified significant dependencies on foreign-sourced legacy semiconductors across multiple weapons programs. It recommended actions to reduce those dependencies. It did not specify how long those actions would take. Building a defense-qualified legacy chip supply chain from scratch requires approximately 5 to 7 years. Qualifying a new chip supplier for aerospace and defense applications requires testing across thousands of hours of operation across the full range of environmental conditions the chip will experience: vibration, temperature cycling, radiation exposure, electromagnetic compatibility. Each qualification program costs millions of dollars and years of engineering time. You cannot simply switch from one legacy chip supplier to another the way you switch phone carriers. The supply chain lock-in is deep, technical, and time-consuming to change. European automakers encountered the commercial version of this problem in 2025. Several major European manufacturers, including Volkswagen and Stellantis, reported that component sourcing negotiations with Chinese semiconductor suppliers had become increasingly complicated by geopolitical considerations. Suppliers were offering longer lead times, requiring larger minimum orders, and in some cases conditioning supply agreements on decisions about manufacturing locations and technology partnerships. This wasn't a supply crisis in the traditional sense. There were enough chips. They were just becoming harder to access on terms that didn't carry strategic strings. European manufacturers lobbied their governments for support. The requests weren't framed as technology competition. They were framed as supply chain survival. The distinction matters. When a company asks for help competing technologically, the political calculus is complicated. When a company says it cannot build its core product without access to components that a geopolitical competitor controls, the calculus becomes simpler and more urgent. The European Semiconductor Strategy, announced in 2023 and updated in 2024, committed 43 billion euros to building European chip manufacturing capacity. The majority of that investment was aimed at advanced chips below 10 nanometers. Investment in legacy chip capacity was a secondary priority. This allocation reflected the political appeal of advanced technology over the economic necessity of boring technology. Advanced chips make for better press releases. 28 nanometer microcontrollers don't generate the same headlines. But 28 nanometer microcontrollers are what European car factories need to stay open. The historical parallel that clarifies the strategic logic goes back further than most semiconductor analysts reach: the oil shock. When OPEC imposed its embargo following the Yom Kippur War, the immediate economic impact was straightforward. Oil prices quadrupled. But the deeper lesson took longer to absorb. Western economies had spent 2 decades building industrial infrastructure, transportation networks, heating systems, and agricultural supply chains on the assumption that cheap oil would always be available. The assumption wasn't unreasonable. Oil had been cheap and abundant, but the production and distribution of that oil was concentrated in a small number of countries with political interests that could diverge from Western economic interests. The geographic choke point of tanker routes through the Persian Gulf created a point of leverage that OPEC used with devastating effectiveness. The response took years. Strategic petroleum reserves were established, fuel efficiency standards were mandated, alternative energy research was funded, supply diversification was pursued, all of it reactive, all of it expensive, all of it coming after the disruption rather than before it. The legacy chip situation follows the same structural pattern. Cheap, abundant legacy chips flowing from concentrated production in a single country. Industrial infrastructure built on the assumption that those chips would always be accessible, and a growing recognition that the country producing them has strategic interests that may not align with the interests of the countries consuming them. The difference is timeline. The 1973 oil shock was sudden, an embargo announced over a weekend. The legacy chip consolidation has been gradual, a market share shift measured in percentage points per year. Gradual threats are harder to respond to than sudden ones. They don't trigger emergency legislation. They don't mobilize political will. They don't generate the kind of visible crisis that forces action. They just slowly narrow the options available until the crisis finally arrives. And when it arrives, the response timeline is brutal. Chip fabs take 3 to 5 years to build from groundbreaking to production. Qualifying new suppliers for automotive and defense applications takes years beyond that. Even with unlimited funding committed today, the supply chain vulnerability created by a decade of consolidation cannot be resolved in less than a decade of sustained investment. The gap between when the problem becomes undeniable and when the solution becomes operational is measured in years, during which the dependency continues. Some analysts point to the CHIPS Act as evidence that the United States recognized this problem and is addressing it. The CHIPS Act is real. The investment is real. The facilities being built are real. But the CHIPS Act was designed primarily to address advanced chip dependency. The legacy chip problem requires a different response, differently structured, differently funded. Building a 3 nanometer fab in Arizona addresses the AI chip competition with China. It does nothing for the procurement manager at a Michigan truck factory trying to source 87-cent microcontrollers. The policy gap between what was funded and what the supply chain actually requires reflects a fundamental misunderstanding of where the leverage is. Everyone in Washington understood that advanced chips were strategically important. The logic was straightforward. Advanced chips power AI, AI powers military advantage. Military advantage requires technological supremacy. Therefore, advanced chips are the strategic priority. That logic is correct as far as it goes, but it assumes that the systems requiring AI can actually be built and operated. A drone swarm controlled by an advanced AI chip still requires the electric motors, the power management systems, the communication interfaces, the navigation sensors, and dozens of other components that depend on legacy chips to function. The advanced chip is the brain. The legacy chips are the nervous system, the circulatory system, the musculature that allows the brain's decisions to translate into action. Brilliant strategy implemented through paralyzed infrastructure produces no strategic outcome. The F-35 analogy makes this concrete. The F-35 is, by almost any measure, the most sophisticated weapons platform ever produced. Its sensor fusion capability, its stealth characteristics, its electronic warfare systems represent decades of research and hundreds of billions of dollars in development investment. It is designed to dominate any air combat environment it enters. It also has a supply chain problem that the Government Accountability Office has flagged in multiple reports. The aircraft's production and maintenance depend on components sourced from suppliers across multiple countries, including countries whose long-term strategic alignment with the United States cannot be assumed. The specific components and suppliers involved are classified. The general vulnerability that America's most advanced weapons platform has supply chain dependencies that could be exploited is documented in public oversight reports. This is the second irony of the legacy chip story. The United States designed the world's most advanced weapon systems, then built global supply chains to produce them as efficiently as possible. Efficiency and strategic resilience pull in opposite directions. Efficiency says, source components wherever they're cheapest. Strategic resilience says, source components wherever supply is most secure, regardless of cost. For 4 decades, efficiency won. Because strategic resilience is expensive and the strategic risks seemed manageable. They seemed manageable right up until they didn't. The 2021 semiconductor shortage was the first visible demonstration that the efficiency-first approacher carried costs that weren't visible in normal operating conditions. When COVID-19 disrupted factory operations in Taiwan and Southeast Asia simultaneously, the just-in-time supply chains that had been optimized for efficiency had no buffer to absorb the disruption. Automotive factories shut down. Consumer electronics faced months-long waiting lists. Medical device manufacturers scrambled for alternative suppliers. The shortage was geographically caused by pandemic disruptions, not by deliberate strategic action. But it revealed what deliberate strategic action could achieve. If pandemic disruption caused that much economic damage, how much damage could a deliberate supply restriction cause? And if the supply consolidation that followed those disruptions concentrated production further in China, what leverage does that concentration create? Those questions are being asked in defense ministries, in parliamentary committees, and corporate boardrooms across the Western world. The answers are generating policy responses. But policy responses take years to translate into changed supply chains. And changed supply chains take years to translate into reduced dependency. In the meantime, the automotive industry is negotiating chip supply agreements with suppliers who operate in a country whose government can, if it chooses, direct those suppliers to prioritize domestic demand. In the meantime, defense contractors are maintaining weapon systems using components that flow through supply chains with geographic concentrations they cannot fully map or control. In the meantime, the gap between where chips are made and where strategic interests align continues to widen. Japan recognized this dynamic earlier than most Western countries. Following the 2021 shortage, the Japanese government committed approximately $6.8 billion specifically to legacy semiconductor manufacturing capacity, not advanced chips, legacy chips. The explicit rationale was that Japan's automotive industry, which represents approximately 3% of Japanese GDP, could not sustain production without reliable access to mature node semiconductors. Renesas, a Japanese chip manufacturer that supplies microcontrollers to virtually every major global automaker, received direct government support to expand legacy chip production capacity. The decision was economically irrational by pure market logic. Legacy chip production is a low-margin business facing intense price competition from Chinese manufacturers with government subsidies. Investing in that business without subsidies doesn't generate competitive returns. But Japan's government decided that the cost of the subsidy was less than the cost of automotive industry disruption if supply was severed. That calculation is strategic, not financial. It represents exactly the kind of decision that markets cannot make and governments must. The United States has been slower to reach the same conclusion. Domestic legacy chip production capacity declined significantly between 2000 and 2020 as manufacturers shifted investment to advanced nodes and outsourced mature node production to lower-cost regions. Rebuilding that capacity requires overcoming the same economics that caused it to decline. Nobody builds a 28 nanometer fab in Ohio to compete commercially with Chinese fabs running on $30 billion in annual government subsidy. They build it because the government decides that supply security is worth the cost premium. That policy decision is still being made in slow motion in Washington. The strategic picture that emerges from these supply chain realities is not comfortable for Western defense planners. High technology military supremacy has historically been measured in the sophistication of the systems deployed. More advanced radar, faster jets, smarter missiles, better communications. The implicit assumption was that technological sophistication would remain accessible as long as the design capability existed. That assumption depended on supply chains that could reliably deliver the components those sophisticated systems required. Legacy chip consolidation challenges that assumption at the most basic level. Not by threatening the design capability, American engineers still design the most advanced weapon systems in the world, by threatening the production capability, because you cannot produce the weapons those engineers design without the components that flow through supply chains increasingly concentrated in a single country. High-tech supremacy implemented through vulnerable supply chains isn't supremacy. It's potential that cannot be reliably actualized. The defense industrial base has begun responding to this reality. The Pentagon's 2022 semiconductor supply chain review led to specific programs aimed at qualifying domestic and allied nation suppliers for defense critical legacy chips. The National Defense Authorization Act has included provisions directing defense contractors to audit their Tier 2 and Tier 3 suppliers for foreign sourcing concentrations. Some weapons programs have initiated redesign efforts to substitute legacy chips that have become supply chain exposed with components from more diversified sourcing. All of these efforts are real. All of them are also slow. Redesigning a weapon system to use a different chip requires qualification testing, software updates, and regulatory approval processes that take years, even when the effort is urgent. The gap between the recognition of vulnerability and the resolution of vulnerability is where strategic risk accumulates. The semiconductor industry itself has begun adapting to the shifting landscape. Texas Instruments, which manufactures analog chips and microcontrollers at mature nodes, has announced significant capacity expansion in the United States. NXP Semiconductors, a major automotive chip supplier, has restructured its sourcing to reduce concentration risk. Microchip technology has expanded production at its Arizona and Colorado facilities. These are market responses, driven by customer demand for supply chain diversification after the 2021 shortage made the risks visible, but market responses move at the pace of investment return calculations. Strategic risks move at the pace of geopolitical decisions. Those paces don't always align. The consumer electronics industry offers a preview of what happens when they don't. In 2019, the United States placed Huawei on the Entity List, restricting American companies from selling components and technology to the Chinese telecommunications giant. Huawei responded by accelerating its own chip design capability, sourcing from non-American suppliers, and building domestic alternatives where possible. The restrictions created genuine pain for Huawei in the short term. They also accelerated Chinese investment in domestic semiconductor capability in ways that may create more significant competition in the medium term. The legacy chip story follows a related dynamic. Western restrictions on advanced chip exports to China have been consequential for China's AI development. They have also provided strategic clarity that directed Chinese investment toward exactly the semiconductor segments where Western supply chains are most exposed. If the West won't sell advanced chips to China, China will sell legacy chips to the world, on terms that gradually shift supply chain dependency in China's direction, at prices that gradually eliminate the commercial viability of competing Western production, until the dependency is comprehensive enough that disruption becomes a policy option rather than a market accident. The historical parallel isn't just 1973, it's also the rare earth minerals story. In 2010, following a maritime dispute, China temporarily restricted rare earth exports to Japan. Rare earths are materials essential for manufacturing electric motors, wind turbines, and weapons guidance systems. China controls approximately 60% of global rare earth mining and over 85% of global rare earth processing. The temporary restriction lasted only a few months and was never fully implemented, but it demonstrated the leverage that supply concentration creates. Japan responded by funding rare earth recycling programs, investing in alternative source development in Australia and Canada, and reducing its per-unit consumption of rare earths in manufactured products. 15 years later, Japan has meaningfully diversified its rare earth sourcing and reduced its vulnerability to Chinese supply concentration. The process took 15 years of sustained, expensive effort. The legacy chip diversification effort is beginning from a more concentrated starting point and facing stronger economic headwinds from Chinese government subsidies. The timeline for meaningful supply chain resilience, absent a shock that forces emergency investment, is measured in decades, not years. The question the global industrial economy faces is whether the disruption that forces emergency investment will arrive before or after the dependency becomes so deep that the cost of building alternatives exceeds any realistic political commitment. That's not a rhetorical question. It's a strategic planning question that defense ministries, automotive executives, and semiconductor policy analysts are trying to answer right now. And the answer depends on decisions being made in research facilities, in Beijing, in budget committees in Washington, in procurement offices in Stuttgart and Detroit and Seoul. Decisions about whether to prioritize short-term cost efficiency or long-term supply security. Decisions about whether to treat legacy chip sourcing as a procurement question or a strategic question. Decisions about whether the cost of building supply chain resilience now is acceptable compared to the cost of operating without it later. The 1973 oil shock eventually produced those decisions, but only after the disruption made the cost of delay undeniable. The rare earth restriction of 2010 eventually produced those decisions, but only after the leverage was demonstrated. The legacy chip dependency hasn't produced a moment of undeniable disruption yet. The 2021 shortage came close, but it was caused by pandemic disruption, not deliberate supply restriction. It created pain, generated reports, and prompted policy discussions. But it didn't create the kind of sustained crisis that forces the expensive, difficult, multi-decade investment required to genuinely diversify a supply chain. That moment may come from a geopolitical event that disrupts Chinese semiconductor exports broadly. It may come from a deliberate restriction targeting specific countries or industries during a period of strategic tension. It may come from the gradual accumulation of smaller disruptions that collectively shift the calculation about how much supply chain concentration is acceptable. Or it may come from something nobody is currently modeling. Supply chain history suggests that the disruptions that matter most are the ones that weren't specifically anticipated. What is anticipated is the structural vulnerability. The global industrial economy, including its automotive sector, its consumer electronics production, and its defense manufacturing base, depends on legacy semiconductors produced overwhelmingly from a concentrated geographic and political zone. The chips are cheap, reliable, and abundant. They are also increasingly produced under conditions where supply security cannot be assumed with the same confidence that characterized the supply chains of the previous 2 decades. That's not a prediction of disruption. It's a description of exposure. And exposure, as supply chain analysts and insurance markets understand, doesn't require a specific triggering event to carry economic cost. The cost of exposure is embedded in every procurement decision, every inventory strategy, every capital investment that accounts for supply risk. When the risk premium on legacy chip supply rises, it adds cost to every vehicle, every appliance, every weapon system that depends on those chips. Not dramatically, not visibly, just persistently, embedded in the price of everything the industrial economy produces. The nervous system of the global economy runs on chips designed in the 1990s. Most of them are now made in one place. And the lesson of every choke point in economic history is simple. Choke points that can be closed will eventually be tested. The only question is whether the resilience exists to absorb the test when it comes. The 87-cent chip that stopped a $55,000 truck in 2021 was a market accident. The next disruption may not be. And when it arrives, the factories, the weapon systems, and the supply chains that depend on legacy semiconductors will discover what the automotive industry discovered in 2021, that the most expensive component in any system is the one you can't get, regardless of what it costs when everything is working normally.